how can you understand a little more of what's going on here? Why these things? Well, as you may recall, we used to have this discussion in which you have AX and AY. You could trade for A right and A left. And with those, the angular momentum in the z direction was h bar n right minus n left. This is for a two-dimensional oscillator, but the x and y of the three-dimensional oscillator works exactly the same way. So Lz is nicely written in terms of these variables. And it takes a little more work to get the Lx and Ly, but they can be calculated, and they correspond to the true angular momentum of this particle. It's the real angular momentum. It's not the angular momentum that you found for the two-dimensional harmonic oscillator. It's the real one. So here we go with a little analysis. How would you build now states in this language? You can understand things better in this case because, for example, for n equals 1, you could have a state A right dagger on the vacuum, A Z dagger, and A left dagger on the vacuum. And then you can say, what is the Lz of these states? Well, A right dagger on the vacuum has Lz equal h bar. This has 0 because Lz doesn't depend on the z component of the oscillator, and this has minus h bar. So here you see actually the whole structure of the L equal 1 multiplet. We said that we have at this level L equals 1, and indeed for L equals 1, you expect a state with Lz equal plus 1, 0, and minus 1. So you see the whole thing. For n equals 2, what do you get? Well, you see a state, for example, of A right dagger, A right dagger on the vacuum. And that has Lz equals 2h bar. And therefore, you must have, since you cannot have states with higher Lz, you cannot have a state, for example, here with Lz equal 3. So you cannot have an L equal 3. In fact, for any n that you build states, you can only get states with whatever n is the maximum value that Lz can have, which is something I want to illustrate just generically for a second. So in order to show that, let me go back here and exhibit for you a little of the general structure. So suppose you're building now with n equal n. The total number is n. So you have a state with A right dagger to the n on the vacuum, and this is the state with highest possible Lz, because all the oscillators are AR dagger. So Lz is the highest. Lz, and highest, the Lz is in fact n h bar. Now let's try to build a state with a little bit less Lz. You see, if this is a multiplet, this has to be a multiplet with some amount of angular momentum. So it's going to go from Lz equal n, n minus 1, up to minus n. There are going to be 2n plus 1 states of this much angular momentum, because this has to be a multiplet. So here you have a state with 1 unit less of angular momentum, A right dagger to the n minus 1, times an AZ dagger I claim that's the only state that you can build with 1 unit less of angular momentum in the z direction, because I've traded this AR for an AZ. So this must be the second state in the multiplet. This multiplet with highest value of L, which is equal to n, corresponds to an angular momentum L, little l, equals n. And then it must have these 2n plus 1 states, and here is the second state. So this is Lz equals nh bar, and here n minus 1 h bar. And I don't think there's any other state at that level. Let's lower the angular momentum once more. So what do we get? A right dagger, n minus 2, az dagger squared. That's another state with one less angular momentum than this. This, in fact, has n minus 2 times h bar. Now, is that the unique state that I can have with 2 units less of angular momentum? No. What is the other one?
AR to the n minus 1 AL.
Correct. That lowers it. So here you have AR to the n minus 1 A left on the vacuum. That's another state with 2 units less of angular momentum. So in this situation, you have a funny thing has happened. And here is why you understand the jump of 2. This state, you actually, if you're trying to build this multiplet, now you have 2 states that have the same value of Lz, and you actually don't know whether the next state in the multiplet is this or that or some linear combination. It better be some linear combination. But the fact is that at this level, you found another state. So this multiplet will go on, and it will be some linear combination. Maybe this diagram doesn't illustrate that. But then you will have another state here, so some other linear combination that builds another multiplet. And this multiplet has 2 units less of angular momentum. And that explains why this diagram always jumps. It always jumps 2. And you could do that here. If you try to write the next things here, you will find 2 states that you can write. But if you go 1 lower, you will find 3 states, which means that at the next level, you build another. You need another state with 2 units less of angular momentum each time. So pretty much that's it. That illustrates how this diagram happens. The only thing we haven't answered, and you will see that in an exercise, is how could I have understood from the beginning that this would have happened, rather than building it this way, that there's this thing. And what you will find is that there's some operators that commute with the Hamiltonian that move you from here to here. And that explains it all. Because if you have an operator that commutes with the Hamiltonian, it cannot change the energy. And if it changes the value of L, it explains it, why it happens. So that's something that you need to discover. What are these operators? I can give you a hint. An operator for the type AX dagger AY destroys a Y oscillator, creates an X one. It doesn't change the energy because it adds one thing and loses one. So this kind of thing must commute with the Hamiltonian. And these are the kind of objects. There are lots of them. So surprising new things that commute with the Hamiltonian. And there's a whole hidden symmetry in here that is generated by operators of this form. So it's something you will see.